Okay, we are live again. So welcome everybody to the Law Physics webinars. So today I am the host, Roberto from Universidad Católica del Norte. Today is a very nice webinar indeed because the speaker of this webinar is going to be Luca Visinelli. He's postdoc at the GRAPPA Institute in the University of Amsterdam in Netherlands. But before he was postdoc at Norte at the Stockholm University. And he got the PhD from the Utah University. So Luca, he is present, he's going to talk about the astrophysics with axion minicluster and axion stars, sorry. So Luca, please, you can start your webinar, and welcome to the Law Physics webinar cycle.
Thanks, Roberto. Thanks for the organizers of Law Physics. It's a great format that I love to follow, and I'm glad to give a talk today on my developments and my research. So I'm going to start sharing my desktop, and you should be able to see my presentation now. Is that correct?
Yes, Luca.
Okay, very good. So I go along. Okay, good. So I'm currently a postdoc at GRAPPA, and today I'll talk about axion miniclusters and axion stars, which topics. First of all, I would like to give an advertisement. I just finished a review on the QCD axion on models of this elusive and hypothetical particle, nevertheless very interesting particle to be studied, along with Luca Di Luzio, this person on the right, Maurizio Giannotti, who's professor in Berry University in Miami, and Enrico Nardi, who's a chief scientist in Frascati near Rome. So basically, if you have any questions on what the QCD axion is, this review now is out, and we just submitted it to physics report. So this is my outline. I would first spend roughly 10 minutes on the QCD axion as a dark matter candidate. I'll also review briefly what dark matter is. Then I'll focus between 10 and 15 minutes on axion radio astronomy, including axion miniclusters. And then I'll spend 5 to 10 minutes talking about what we can learn from gravitational waves. I decided to condensate the talk in 30-35 minutes, so there will be enough time for questions that might arise from the chat or our discussion. These are the papers in which, from which I based my talk today. So we know that we have overwhelming evidence for the existence of dark matter at different scales in astrophysics and in cosmology. First of all, well, we know that the rotational velocity curves of galaxies differs from what we expect from the visible disk. Instead, we have a rotational curve that doesn't match what we would expect just from looking at the luminous content of a galaxy. But we have, in order to match with data, we have to assume that there is way more mass than what we see. This is the dark matter interpretation of this mismatch between the theory and the observation. We also have evidence at different scales. For example, when clusters of galaxies merge, this is, for example, a bullet cluster, where we see there's more than one gravitational potential, which is in line with what expected from the existence of dark matter, which basically would pass through each other and maintain their potential wells, as opposed to gas, which sticks in the middle. We also have evidence from cosmology. So we see that the peak in the cosmic microwave background are fit nicely if we assume that dark matter is already playing its role and deepening the potential well at the time of recombination. We also need dark matter in order to seed structure formation later, to give enough time for the galaxies, as we know, to form. So what does have this to do with the axion? Well, for this, I have to jump into particle physics from cosmology. And I first have to discuss what the axion is. So we know that the QCD sector of the standard model allows for a term which is of the form of this trace, E dot B, where E and B are the electromagnetic counterparts of the gluon field. Alpha S is the strong force coupling, and the theta is a new parameter, which we expect to be of order 1, and it controls the matter-antimatter asymmetry in QCD. This is why it has some effects that are visible in principle. For example, it would give the neutron electric dipole moment, which we don't observe. And this is why we can place upper bound on the absolute value of this quantity, which has to be smaller than 1 part in 10 billion. So we can live with this, or we can dig deeper and look for why one quantity, which in principle is of order 1, is now constrained to be less than 10 to the minus 10 by experiments. This is the axion solution. So for the QCD axion, to get to the QCD axion, we first have to promote this field, this parameter theta to be a field, which roll to 0 dynamically. So it's the dynamics itself that constrains the field to be 0, to be observationally small. This is the solution first proposed by Pechet and Quinn in 1977. And it was then realized that, it was then realized that this theory comes with a quantum, which is the axion. So this was actually independently proposed by 2 Nobel Prizes, or 2 currently laureate, Weinberg and Wilczek, who in 1978 then showed that the Pechet-Quinn solution of the strong CP problem comes along with a new boson, which is called the axion. And then the Lagrangian, what we saw, that is legitimate from the standard model, actually converts into this Lagrangian in which the axion field pops up, makes it present. This is a dimension 5 operator, so it has to be, it comes up with a new energy scale, which is called the axion energy scale. It's this quantity F. The axion mass is inversely proportional to F, as we see in this box here. The axion mass is of order of the lambda QCD square, so the QCD confinement scale square, which is of the order of 200 MeV, over the value of F. Since we expect experimentally F to be larger than 10 to the 9, 10 to the 10 GeV, this pushes the axion mass to be below the milli electron volt, so extremely light particle. This is a 1-parameter theory, and it's falsifiable. So this is a plot that comes from our review that just came up, but this plot has been proposed in already in different other different reviews, and it shows the axion photon coupling on the y-axis in units of invert GeV as a function of the axion mass in electron volt. So we see that there are different constraints that can be placed on this parameter space, with the constraints bound by the solid lines being experiments that have already placed bounds, whereas dashed line border proposed or future experiments, future reach of current experiments. The axion photon coupling comes from this anomaly diagram, in which the axion couples to 3 level to fermions, and then this fermion can close and make a loop, a fermion loop. And it's required that these fermions also couple to photon. So we have an axion photon-photon coupling. We can distinguish between roughly we can distinguish between vertical lines here, which are experiments that exploit cosmic axions. So axions that are dark matter, which I will explain more in a minute. So, for example, ADMX or Clash. So these are axion haloscope. They use the axions that are in the galactic halo and they look for them by trying to convert them in a magnetic field, which is one of these two photons, and making looking for a signal. So the other photon in the Feynman diagram. Instead, the horizontal lines are axion haloscope. So they don't rely on the axion being the dark matter. They look for axions that are produced in the sun. For example, IAXO is a proposed experiment that would be designed for this, looking for this particle being produced in the sun. The QCD axion is one particular line for which the axion photon coupling is proportional to the axion mass. So once you choose your theory for the axion, then you can compute this diagram here. And you discover that G, the axion photon coupling, is proportional to the axion mass M. This draws a line in this diagram, and then we can look for this particular model. We can hope that our experiment is sensitive enough so that we can probe this model. And the interesting axion model lie in this yellow band here. So far, ADMX has been placed bound on this. And there are many other experiments that also propose to search for this particle in the near future. So let's see, how do we now account for the axion as being the dark matter particle, since it's so light? First of all, we had to embed it in a higher dimension theory. So for this, we have to introduce a Peccei-Quinn field, phi, of which the axion is the angular variable here. It appears in the exponent, normalized by the axion decay constant f. Then the radial part can be split into what is the vacuum expectation value, f, plus an oscillation, a radial oscillation about this value, f. So this is exactly as the Higgs mechanism, is a similar idea. In fact, we expect that the Peccei-Quinn potential develops a Mexican hat potential well, in which the radial mode sits at the bottom of the true potential when the minimum develops, when the temperature of the universe is of order f. And then the axion is the angular variable. It sits anywhere in this circle. So it takes, and the value of a over f takes any value between 0 and 2 pi. And in fact, it doesn't appear in this Mexican hat potential. What then happens, which is remarkable and peculiar just for the QCD axion, is that at even lower temperature, so when the universe cools down at the order of the QCD energy scale, we have additional effects. We have non-perturbative effects that come from the interaction of the axion field with the gluons, which tilts this Mexican hat. So now all of these values between 0 and 2 pi are no longer equivalent. There is one true minimum in which the axion fields would start to move, to roll down, and in this movement it would oscillate. It would then oscillate about this true minimum. And it is these oscillations that store the energy density that behave as the dark matter. So this is an idea which is slightly different from the WIMP mechanism, so from the other archetype of dark matter. For WIMPs, the energy density is stored in the mass energy of the particle. For the axion, the energy density is stored in the oscillations of the axion field. The details at which this potential is, this additional potential from the QCD interaction is turned on are still debated and rely on lattice simulations. What I just described is known in the literature as the vacuum realignment mechanism. So it leads to this equation of motion for the axion, in which basically resembles that of a damped oscillator. We have the acceleration of the axion field, a damping term where h is the Hubble rate, and we have the mass that acts as the frequency, times a sign, which makes this oscillations non-harmonic. So at very early time, for very early we mean when h, the Hubble rate, is larger than the mass of the axion. So we can put a place of watershed between the moment in which h is much larger than m. So for times smaller than t os, in which the axion dynamics is frozen and the energy density is constant. And the moment at which the axion mass starts to matter, and for which the axion field is set into motion, and the energy density scales as the scale factor of the universe to the -3, so as the inverse volume. It behaves as dark matter. The history is even more complicated than this, because there are topological defects. We are talking about a complex scalar field. And in this regime, we expect that the field develops a string network. So it develops domain walls, strings, and other topological defects already when the Pecchin-Queen symmetry breaks. This because if inflation doesn't play a role in this scenario, the Pecchin-Queen symmetry breaks in different ways, in different patches of the universe. So the axion field takes different values in different patches. These patches would then attach to each other. And at the borders of these patches, there would be a potential difference. We see this in numerical simulations. So this is from my colleague Javier Redondo, in which we have a 2D slice of a 3D simulation. The axion field, theta, takes any value between -pi and pi, where -pi and pi being white, while the value 0, the minimum of the axion field, would be black. And we see that as the time evolves, there are regions like this region here that I highlighted, in which the axion field takes all of the value going from white to color, to black, color, then white again. So it ranges all of the values between -pi and pi, circling around this dot. This dot, which I remember is a dot on a 2D slice of a 3D box. So this is actually a string. It's a 3D string, which is a compact, localized energy distribution, which we cannot get rid of if not for the dynamics. We see that when the axion field acquires a mass at a temperature of the order of the QCD phase transition, This string network is dissipated by the formation of the mailing walls. And during this evolution, the string network constantly evolves and radiates axions as quanta of the field, and modifies the energy density of the axion dark matter. So this mechanism has also to be taken into account when dealing with when assessing the value of the axion dark matter today. So now let's go to our compact objects, axion miniclusters. We see that if we compute the energy density stored in the oscillations of the axion field, from, for example, from the picture that I showed before, there are spikes. So there are regions in which the energy density is large compared to the mean value of the energy density. These is 2D slice from this paper by Kolb and Tachev in 1996, which studied this phenomenon numerically. This spike of energy density would later, at matter radiation equality, collapse gravitationally and form what are known as axion miniclusters. So these are dense structures, dense objects made of axions, which have a typical mass of the order of the asteroid mass, 10 to the minus 10, 10 to the minus 11 solar masses, and a radius which is comparable to the distance between the Sun and the Earth. So you would think this is a quite dilute object, not diluting an asteroid over a volume equal to the volume that has a radius of this size. Yet this energy density is 100,000 to 1 million larger than the average dark matter density. So even if these objects are so dilute, they still store a larger fraction in energy density than what we expect from the local dark matter abundance. These objects have been recently studied in numerical simulation from embodied simulation. So the idea is to take the simulations that I showed earlier for the Pacheco field as initial condition at matter radiation equality, and then follow the evolution of this overdensity as structure formation evolves. And this leads to a whole statistics of these objects. So we discovered that this is not a monochromatic spectrum. It's not that all of the axion miniclusters have a mass of the order of 10 of asteroid mass. This is actually upper bound. Miniclusters are formed in all mass ranges with some halo mass function, and then structure formation would form even larger axion minicluster by hierarchically merging these building blocks together. This is the idea that comes then for what I'm working on, which is axion radio astronomy. This idea has been used already to study the conversion of galactic axions, so axions that are not bound into structures, into minicluster, but just make up the ambient dark matter that we see. And since these particles convert into photons in the presence of a magnetic field, why not use the magnetic field that's hosted by a neutron star? So neutron stars are environments, possess an environment in which dark matter axion would fall and convert into radio waves that are potentially observable at Earth. Why radio? Because this is the energy of a photon associated with the rest mass of the axion, which basically we can say it has a mass of the order of the gigahertz, if it is the dark matter. We know that for a neutron star, well, there are models for the magnetic field around the neutron star. The most studied of which is the Goldreich-Julian relation, which is a self-consistent relation that tells you what the magnetic field is and what the number densities of charged particle is around a neutron star. So both of these quantities are inevitable around a rotating neutron star. And axion-photon conversion would happen when the plasma frequency associated with the distribution of charges around the neutron star would equal the axion mass. So we expect, if we look at a neutron star, we expect to see some radio waves coming from it if there is axion dark matter falling into the environment of this neutron star. This is the setup. We have a neutron star that rotates around its z-axis with some magnetic field oriented in some m direction. We are at Earth at some distance from this neutron star, and we see this signal. So we can place a bound on the axion-photon coupling versus axion mass space that I showed earlier. We can place a bound based on the sensitivity of radio astronomy that we can exploit. A similar idea can be used for not for ambient galactic axions, but for axion miniclusters. So for this, we have first to assess how many axion miniclusters are there today. So the M-body simulation that I discussed before give us what I call the initial Halo mass function. So we know how the number density of axion miniclusters is distributed with their mass. In the case in which we have an axion-only universe. And in this universe, there is also stars. There are different potentials that in which the Milky Way evolve, and this would disrupt these fluffy environments made out of axions. So for this, in order to assess this, we run an M-body simulation in which our axion minicluster collide with ordinary stars in the galaxy. And we see, as a function of the galactocentric distance, how many of these axion miniclusters survive to date. We see that, so given this dashed vertical line as the position of the solar system in the galaxy, we see that in our model, most of the axion miniclusters have survived to date in the vicinity of the Earth. But then, as we move towards the galactic center, the survival probability quickly drops to 0, and within 1 kiloparsec from the galactic center, there are no axion miniclusters because there are just too many stars. All of these axion miniclusters have been swollen, they have been disrupted tidally by the encounter with nearby stars. So if we are looking for a signal from this object, we can only look from, in the vicinity of the solar system. So my collaboration includes Thomas Edwards, who's currently a postdoc in Stockholm and Stockholm University, Bradley Kavanagh, who's currently in Spain, and Christoph Weniger here in Amsterdam. On top of the survival probability, which is the blue line, we also have the interaction probability here. which is the orange dashed line. What is this interaction probability? It's the probability that a neutron star interacts with an axion minicluster, given some cross-section that depends on the relative size of the two and the gravitational focusing that they might have. And we see that because of the shape of the survival probability of axion miniclusters, this interaction probability peaks at a radius, a galactocentric radius of the order of a few kiloparsec, around 3 kiloparsec. It then drops for inner galactocentric radius because the survival probability drops. And it also drops at larger values because there are fewer neutron stars. So the chance that an axion minicluster hits a neutron star as we move far away from the galactocentric radius, so far away from the disk, the center of the disk is more and more faint. Okay, so we see how these encounters are distributed. Most of the objects of the neutron star are distributed in the galactic disk, so which is this line here. Whereas the axion minicluster make up the halo of dark matter, so they are distributed spherically, evenly over the whole sphere. We see basically that we come up with a donut-like, ring-like shape, which is placed on the galactic axis, in which we have basically the most chances to detect axion minicluster neutron star in encounter. In our simulation, we also check what the duration of the encounter is as a function of the peak flux. And we notice something interesting. So we have basically two populations of axion miniclusters that give rise to two different types of signal. One population gives rise to relatively short and bright signals, and these are due to the axion miniclusters that are the most dense, the densest one. There is also a population of axion minicluster that gives rise to a signal which is fainter and it lasts longer in duration, coming from axions which are less dense, axion minicluster which are less dense. This is because some of the axion miniclusters have been disrupted and they make up this second population. So they have lost some of their mass. Whereas the axion miniclusters have not been disrupted and still there in the halo, when encountering a neutron star, give rise to the most bright fluxes that we can observe. So these are the ones that we hope to observe in the future if some search of this object with axion radio astronomy would take place. I have here a video that would show this. So now I'm going to do something that shouldn't be done, like getting out of the presentation. But I want to show you how we expect one of these encounters to look like. So this is a very preliminary simulation again. We expect to have a background of a signal that with time that gives rise to some signal in microlensing, due to the fact that we have many low-density axion miniclusters. So these are puffy, and the neutron star take a lot of time to transverse them. But we also have, from time to time, some encounter with some much denser and so much smaller axion miniclusters, which also gives rise to these peaks that we can hope to observe. Let's go back to the full screen presentation. Okay, so I now want to talk about another topic, which is gravitational waves from these cosmic strings. So I showed you that in simulations of our Pechequin field. Let me take a sip. The simulation of this Pechequin field, complex field, we expect a network of strings to develop. This is actually fairly known already from the 80s, just from simulation of complex scalar field that don't necessarily are the Pechequin field. So what happens here? We have at all scales strings, so strings with the length of the order of the horizon, the Hubble horizon, constantly enter the size of the horizon and are sliced up by the fact that they intersect with each other, and they might also form closed loops which vibrate. They have some vibration modes that radiates energy density away in, it depends on the theory, in Goldstone bosons or axions, and gravitational waves, and this makes these loops shrink. This is observed in numerical simulations of the string network, and this would make basically the string network lose energy into both axions and gravitational waves. In the theory of the QCD axion, the amount of gravitational wave is subdominant with respect to what the strings radiate into axions. So you never hear about gravitational waves from the QCD axion string network. Moreover, the string network of axions dissipates as the QCD phase transition because of domain walls. So it doesn't last until today, and this makes the this amount of radiation even less predominant, because it then whatever is left from this radiation is redshifted as the inverse power to the fourth of the scale factor. So much faster than matter, and we don't observe it today. Now, is it really true? Is it really true in every cosmology? So let's see, what do we know actually about the standard cosmology? We know that there is some Planck area in which inflation might occur, some gut area in which inflation might have occurred here, but then our inflation ends, we enter into a reheating stage that goes into the radiation part of the universe, in which relativistic degrees of freedom take place. Then these particles would cool down because of the expansion of the universe. We enter into nucleosynthesis. And then when the universe cools down again, we allow for the nuclei to form. This is the last scattering surface. This is where our CMB forms. And now we enter the era of atoms, which clump and make galaxies today, and here we are. Point is that we have a direct evidence of this picture only up until the first 3 minutes. So we don't know what happens in the first 3 minutes of the universe. So what happens before Big Bang nucleosynthesis? This is a big black box from which we don't have relics, we don't have evidences. So we can say that our standard cosmological scenario, in which we have a radiation-dominated universe that transitions into matter-dominated universe, and then to our present one, which has a considerable amount of dark energy. Only we can have this fiducial model only up to some temperature Tmax. So maybe, this Tmax is 10 MeV, maybe it's 100 MeV, maybe it's 10 GeV. We don't know how much we can push this this picture up into this black box. So we can think about other possibilities, other non-standard cosmologies in which this Tmax varies. This has been done, for example, by considering the spectrum of gravitational waves as a function of their frequency, and considering how much gravitational waves are shed from are released from a cosmic string network. So in this plot, we have a string network that radiates gravitational waves, mainly gravitational waves, up until today. In the standard cosmology, we would see this black line. So this black solid line is the expectation of this model in the standard cosmology. But if the universe is standard cosmological model only up until some temperature Tmax of the order 1 GeV, then this spectrum would cut, following instead this dashed line. And if the Tmax is even lower, 10 MeV, the spectrum would cut to this dot line. So these three scenarios, standard or some modified cosmology that takes place before, when the universe was hotter than Tmax, can be actually probed in the near future from gravitational wave detectors, such as LISA or BBO. They would be able to tell what the spectrum of gravitational waves from possible cosmic string network is. The nice thing, the sensational thing, is that this can be done even for axions. So this is a project I've done with a master student, Niklas Lamberg, in Uppsala last year. We see that basically under certain conditions, we can also see, we can hope to see gravitational waves from axion strings. So this is a network of axionic strings. So it's fundamentally different from what I discussed in the previous slide in two key factors. First of all, these are axionic strings. So they mainly radiate into axions. You don't expect a large amount of gravitational waves. And the axion string network only lasts until more or less the QCD phase transition, so around 200 MeV, and then it dissipates. Yet, there is hope to detect the amount of gravitational waves that comes out of this model if the universe is non-standard cosmology down to temperature of 1 MeV or 5 MeV. So if we really push the parameter space of this model. Okay, so these are my conclusions. Basically, there is a lot to do in these models for the axion, for the scalar fields in general. We have to keep working on details, making estimates, and push for collaborations, even larger collaborations that would take together researchers in the theory and in the observation together in order to look for these particles from alternative point of view, not just from the laboratory, but looking for these type of different imprints that are complementary. Thank you.
Thank you very much, Luca, for your webinar. Your seminar. It was very nice. So for those that are following the live streaming of the Luca's webinar, please, you can start to write your questions. We're gonna go there soon to address that. don't forget to the people that is following the webinar from the first time to subscribe to the YouTube channel and also to follow us in the different social networks like Facebook and Twitter. And so we go back to Luca and we start with some few questions first from the audience that is here. I don't know one of the participants, if some of them have questions. Otherwise, meanwhile, I'm gonna be checking what is in the YouTube chat. So for that,
I had one question or a couple of questions.
Okay, Javier, please.
Yeah, well, I mean, maybe I'm getting completely wrong the scales because I don't have any kind of intuition of how big are these objects. But how do they compare to usual dark matter subhalos that you see in embodied simulations? And related to that, probably they are much smaller and they had a smaller tidal effect. But is there any possibility of observing these kind of things in through these reactions in stellar streams, like things like Gaia or things like that, or they are too small to produce any effect?
Okay. Yeah. So okay, there are different scales. So in terms of WIMPs, we expect the WIMPs to form this type of clumps at larger and heavier scales, because the WIMP form clumps through the free streaming length. The free streaming occurs at the tens of MeV temperature in the early universe. And in that case, the mass enclosed is much larger than what we expect for the axion, because they form at for the axion it forms earlier than for the WIMP. So I'm not talking about these the seeds for WIMP called dark matter. But then besides these lengths, both the QCD axion and WIMP would behave at a larger scale as cold dark matter. So you would not see the difference until you go to such a low scale, so such a high K in mode, which means that the halos 10 to the 5, 10 to the 6 solar masses that you observe cannot distinguish between on the particle perspective in case of cold dark matter.
Okay, and well, I don't know if I can ask another question.
Yeah, you can.
No, it's related to this last strings given to observable gravitational wave production that you were talking at the end. So this is also QCD axion, or is a completely? Yeah.
I just used QCD axion. In this talk, I just showed results for the QCD axion. Yeah.
Okay, but then if you are able to observe gravitational waves, I mean, you will have also a larger contribution into radiation. And is that not violating any kind of bit nucleosynthesis constraints on the amount of additional radiation?
Okay. So let's see. And then I would say no, because we still have the QCD axion as the dark matter. So okay, you have basically something I didn't discuss. The axion can come also as a hot component of the universe, depending on its mass. So if the mass of the axion is of the order of tens to hundreds of microelectron volt, the dark matter component, the cold component, is predominant over the dark energy radiation component. Since we are in that ballpark, the amount of dark radiation would still be negligible in these models. Then, of course, if you consider axion-like particles or the QCD axion, which is not the dark matter, and you want to push to heavier axion masses, then you have to be concerned about what fraction of dark radiation you would get out of this model, and then you would also get into bounds from n effective or delta n effective.
Okay, thanks.
Okay, thank you. Is there any question from the audience? Let's wait a bit because we are going to start.
I have one.
Oh, Nicolas, okay, you go.
So it's related to your previous slide where you showed the gravitational wave. So suppose you have a detection in one of these observatories. There's no way to be sure that it comes from a string, right? From an axion string.
Well, yeah. It would, well, if you have say you have a Lisa, for example. So you have to match the spectrum. So you have to match the slope of this curve. And this would already be by itself a huge discovery, because it would tell you we have something new that we, because we have some sort of negative slope that can come up of a string network. Then yes, I would say you have some sort of degeneracy between different models. Mm-hmm.
Okay, see. I also want to ask, what's the physical meaning of this, of the maximum? It's giving you some information about something, I guess. Yeah.
For example, okay. So these spectrum here in this model, at each frequency, basically we observe. So this F is a sort of can convert into the moment at which the gravitational wave is released. So this is why we have different slopes here. Basically, waves between 10 to the minus 8 and 10 to the 1 have been released during radiation domination. Matter radiation equality occurs when this kink appears, and frequencies that are smaller than this 10 to the minus 8 have been released from the string network after that time. This is why I don't have that type of plateau here. I only observe either the radiation dominated part or the modified cosmology part. So this peak is basically the transition between the two.
Okay, thanks.
Okay, so we are going to go some of the questions that we are getting now in YouTube. So Marvin Flores, he's asking two questions. The first question is, when you say that the theory is one parameter, is this parameter the action mass? Because you show a plot where the action mass is proportional to the action photon coupling. Are the other couplings also present?
Yeah. So basically, okay. One parameter theory means that the axion mass controls the axion energy scale F, just because it's inversely proportional to that, but also the axion photon coupling. One thing is that we have different parameters that appear in this vertex. So how the axion field couples to the fermions. This depends on how you embed your axion theory into the standard model. So there are additional parameters. But once you choose your embedment, so this E over N, basically, then your G A gamma depends just on the axion mass. And this is why for a given axion model, G is proportional to M. This is true also for the other coupling, so the axion to the electron and to the nucleons. I hope this helps.
Yeah, I think so. I mean, we can, in the meanwhile, Marvin Flores can write if he like the answer or not. Let's see. No, anyway.
Parameter theory, once you know which embedment you're working on.
Oh, yeah. So I have a question. I mean, for the moment, I have a question. When you were showing these action strings that you were forming in the kind of in the simulation, and by simulation, let's say.
This one?
Yeah, exactly. That was very nice. But do you expect that the action strings has a large effect in the structure formation, or do you expect, for instance, kind of dwarf galaxy to have some population of action strings, action strings in these topological defects there, in which you can get some signature, like taking advantage of the same method that people use for standard for weak dark matter, kind of the same target, galactic center. Okay, the galactic center, you said that it's not possible because the population should be very low, but other object like dwarf galaxy or something like that.
Well, so this simulation is from Javier Redondo. Take credits for this, but I can tell you about your question. The point is that this the peculiarity of this of the axion is that its first is massless, and then it acquires a mass around the QCD phase transition. This makes this string network to live only up to the QCD phase transition. And all of the axions that are radiated during this period, they get in contact with the population of axions from the vacuum realignment mechanism. So from this mechanism here. And they basically share information and share the distribution, the density distribution. Which means that they quickly become thermalized between themselves after the QCD phase transition. So you don't probe this string network at subsequent times. So this string network doesn't exist to date. It doesn't exist during structure formation or during the CMB. This is gone at 100 MeV, basically. If you consider other models with Goldstone bosons, there are massless or just a string network, then it's a different story. You can make simulations with these type of structures in them. But I don't know the details about those because I never worked on those.
Okay, but when you were just the little one, when you were also presenting before this, I guess the possibility to look for neutron stars interacting with the action that are in the environment. So those are more astrophysically searchable, let's say, no?
Yeah. So the story is like basically you have these inhomogeneities in the axion field. These axion field, so these inhomogeneities are seen in the energy density distribution. They're huge. And these translate into these dense clumps, which are called axion miniclusters. The point is that the axion is a subdominant field during radiation domination because it's a cold dark matter. So if you had instead these type of structures, so these density perturbations in the plasma, you would form black holes, primordial black holes. You don't have enough density contrast basically to make black holes, so you make axion miniclusters. And they stay, but they collapse at the matter radiation equality, and they stay to present day. given the embodied simulations that I discussed. So what is missing now is an embodied simulation that takes into account the evolution of the galaxy and the stellar formation and evolution and the merging of the axion miniclusters and how stellar evolution affects this embodied simulation. This is not what we do. We basically have embodied simulation of axion minicluster down to some Z. We take that result from the simulation of Javier and Eggemeyer and Adam, and then we run our model, our Monte Carlo disruption model. So it's a first step towards something more reliable.
Mm-hmm.
Something that's not there yet.
Okay.
So these results for the survival probability are not in the literature at all.
I see.
Mm-hmm. In terms of Monte Carlo. So there are estimates given some analytic results. They're also valid for generically dark matter subhalos. But the whole literature on what these axion miniclusters do is missing. How many of them are there in the galaxies? And this is a demanding question because, first of all, because of our story, like radio astronomy, which seems to be possible, seems that the signal is actually detectable, but also in terms of lensing and in terms of direct detection. So they would play a huge role, and we're just starting to work on this now. Yeah.
Good. So let's say, is there any other question from the audience? I don't know.
Well, I have another one if I can.
Yes, please.
No, it's a bit, maybe a bit more technical. When you are showing these simulations by Javier, I mean, looking at the plot that you had looks like a field theory simulation. But then you are talking about loops that comes from a Nambu-Goto simulation. There are no loops in these field theory simulations.
Mm-hmm.
So it's kind of consistent, all the things that you are saying about radiation, etc. I mean, so how you can conclude something? I mean, you're like kind of mixing parameters from two different simulations.
Okay. The results that I have on this part on gravitational waves are just they're not coming from a simulation. We just did some analytic or semi-analytic model. So we just solved for the equation of motion of the axion field in non-stellar cosmology, and we estimate the amount of gravitational waves out of formulas. So the results don't come out of simulations.
Yeah, but then is where my problem is kind of coming, because you say it's a small fraction before, but I see at your plot, at least the upper curve is around 10 to the minus 8, but integrated is going to be a bit bigger. It's going to be like 10 to the minus 7, 10 to the minus 6. And the bounds on radiation, or if you want, the integrated bound on gravitational waves in the CMB is 10 to the minus 5. So the one of radiation should be roughly the same. There's extra radiation that you can put in the game.
I see.
So you're not so far away from 10 to the minus 5, I have the impression. But I don't know. Let's go back to my question on big bang nucleosynthesis again. I don't know. I have the impression that you're not so far away. But maybe I'm getting completely wrong the numbers.
No, you're right. You're right. I took those bounds into account. I computed afterward, a posteriori, that integral and checked that it was the result was within the bound.
Yeah, but you did it for gravitational wave. My question is about the radiation.
Yeah.
You should get a similar bound for radiation, roughly, not the same order.
So for that, I relied on what other people have done in these models, and which found that basically the dark radiation is not important at the masses at the axion mass. I can send you I'll send you the link, but basically it's the work of Raffelt.
Okay. No, it's just my ignorance. I don't know. Again, I don't control the numbers exactly. So. Okay. Yeah. It's nice to work on that. But yeah, I haven't worked on. I haven't derived the limits myself because working on dark radiation, you have to take into account all of the productions from the gluon plasma. So I just relied on what the literature.
Okay, so we have one more question from YouTube. Percy Cáceres from the PUC in Rio de Janeiro. He's asking is there some mechanism to link the actions from the axiverse to the action string that you show in the last slide? And he's also thanking you for the nice talk.
Thanks. Well, these strings are, these are two different string scenarios, but I would say, well, if your string axion, so a string from the axiverse, basically, if it relates, if you can also relate that to some spontaneous symmetry breaking, you would observe the same network, just at different regimes. So yes, I think in principle it's possible. It's just that when you talk about the axiverse, you're no longer talking about the QCD axion. So in that case, the parameter space opens so much that it's not easy to give solid answers. But in principle, yes, you would have this network just with different with the different dynamics and different parameters that what you expect for the QCD axion. I see something here. Okay.
So
yeah, I hope this answers the question. Otherwise, if there are questions, I can answer them on YouTube.
Okay, so I guess we have to stop here because to keep the format of the webinar cycle. But anyway, you can for the rest of the people that is still interested, you can make comments in the YouTube video of this webinar, or otherwise contact Luca directly personally via email or other ways. So first of all, I want to thank Luca for your webinar. It was very interesting, and we hope to see you again for a follow-up talk in the future. So for the rest of the people that is following the webinars, let me tell you that next week we are going to have another webinar, but this is going to be by Macarena Lagos, that she's postdoc in the Cable Institute for Cosmological Physics. So everybody is invited to follow the webinar, and of course to keep in touch and keep updated with what is happening in high energy physics, astroparticle, cosmology, and all the topics that we used to cover here in this webinar cycle. So for all the people, thank you a lot, and see you in the next time.
Yeah.
Bye to everybody.
Bye. Stop sharing here. Okay.
Okay, we are